we're going to look at rotational dynamics. We're going to start by looking at the relatively simple case of, let's just suppose I have a block of mass M with an applied force of F. What's going to happen? So the first step, we get a free body diagram. In this case, we would write F is equal to M times A. The acceleration would be equal to the force divided by the mass. The next level of review, the next level would be, imagine I've got a pulley, I've got an M1, an M2, and I release this thing, and I want to know what the acceleration is. As per usual, first step is free body diagram, tension up, M1G down, tension in this direction, and then assuming, as we did the beginning of the year, that this is a massless pulley, we can write two equations. We can write M1A is M1G minus T, and I can write M2A is equal to T. Combining these two equations, I get M1A is M1G minus M2A, M1, M2A is M1G, A is equal to M1G over M1 plus M2, which makes sense. You effectively have a force divided by the total mass. Now, let's suppose now since we've learned about moment of inertia, rotational kinematics, let's imagine I have a situation here where I pull down on this pulley, but now this pulley has mass and it has a specified radius. If I take and apply a torque to this thing, it's going to begin to rotate. Since it's rotating, therefore torque must have been applied. So torque is equal to I alpha. And we're going to remember that if this is a disk, that I is just 1/2 mr squared. So I can write the following. Torque is R cross F is equal to I alpha. And in this case, it's just going to look like R times the applied tension, the applied force, is equal to I alpha. And I can rewrite alpha. Remember that alpha is equal to A over R. So I can write RT is I A over R. And we find the acceleration of a point on the line, a point on the string, is equal to R squared T over I. And if you remember that I for a disk was 1/2 mr squared, we end up with T R squared over 1/2 mr squared. The r's cancel out. And we get T over 1/2 m. So again, force divided by mass gives us acceleration. So what's going to happen if I now have a mass on the end of this pulley? So we're going to call that M1. We'll call that M and R. And now I have two free body diagrams. I have the free body diagram associated with the hanging mass, M1G down, in tension. And then I have the tension and the radius vector, which is going to give me torque. This equation here, or this free body diagram here, gives me M1A is M1G minus T, and this gives me I alpha is R times t. I can rewrite that as the tension is I alpha over R. I'm going to take that tension and I'm going to plug it in to this equation, and I'm going to have the following result. M1A is equal to M1G minus I alpha over R. Remember that alpha is equal to A over R, so I can rewrite this as M1A is M1G minus IA over R squared. And then rearranging this, I get M1 plus I over R squared, all times A is M1G. And then the acceleration now is M1G over M1 plus I over R squared. And if we substitute in I for a pulley, this just looks like M1G over M1 plus 1/2 mass of the pulley. So that makes sense. But notice that what we've done here, this result here is really not all that. This result here is really not all that different from what we saw here. In both cases, we have a mass that's being a force that's generating the acceleration of, in this case, two masses, and in the case of the pulley, it's accelerating a pulley and a hanging mass. The interesting part comes in when we now have an M1, I'm going to call that M2, and a pulley which now has a mass and has a radius associated with it. Now I have three free body diagrams. I have T1 coming up here. I have T2 in this direction. And my three free body diagrams give me, well, the first one's simple. M1A is M1G minus T. The M2A is equal to T2. That should be T1. But this is the more complicated one. So what I have is I have a pulley that's being, pulley that has a T2 applied torque in that direction and a T1 associated torque in that direction. So this is going to look like R times T1 minus T2 is equal to I alpha. And probably the simplest way to deal with this is to solve both of my first equations for T. So T2 is M2A, and T1 is equal to M1G minus M1A. Substituting those in here, I'm going to get R times M1G minus M1A minus M2A is equal to I alpha. I'm going to make a couple of substitutions. I'm going to substitute A over R for alpha, and I'm going to bring the R over to the other side, and I'm going to end up with M1G minus M1A minus M2A is I over R squared, we see that again, times A, and then I can rewrite this whole thing as M1G over M1, M2, I over R squared is equal to acceleration. So again, I have the net force on the top, and then I have effectively the total mass, and I'm going to put effective there because what we're doing is we're accounting for the inertia of the pulley. Again, if I substitute in the value for a disk, this looks like M1G over M1, M2 plus 1/2, what we'll call big M, is equal to the acceleration. So when I add a pulley that has both mass and a radius, the only impact is that it just means I have to account for the force or the torque that makes it accelerate. So suppose now I have a pulley on top of here. I have a mass on this side, and I have a mass on this side. We'll call that M1. We'll call that M2. Just like we've done before, the first step is to determine a direction of acceleration. I'm going to have it go in this direction for acceleration. I'm going to call that T2. I'm going to call that T1. And I'm just going to write my equations out again like I've done. M1A, forces on A are M1G down minus T1 up. M2A is now T2 minus M2G sine theta. And then we have R times T1 minus T2 is I alpha. And again, we're just going to do the same. We'll do as we've done before. T1 is equal to M1G minus M1A. T2 is equal to M2A minus M2G sine theta. Plug that into here, and if you do it all out, you should end up, and you should check this on your own, you end up with the net force, M1G minus M2G sine theta divided by the effective mass, M1, M2, I over R squared. The one last classic problem is the Atwood's machine, where I have a pulley, I have an M1 here, I have an M2 here. I'm going to guess the direction for acceleration. We have a T1 up, we have a T2 up, and again, I just write my equations. M1A is M1G, it's going to be T1 minus M1G, because I've assumed acceleration is in the clockwise direction. M2A is going to be M2G minus T2, and then R times, in this case, I've got to be careful, I've got a T2 minus T1 is equal to I alpha. And again, I can solve this whole thing out just like I've done before. You should convince yourself that the solution is going to be of the form A is equal to M2G minus M1G over M1, M2, I over R squared. I didn't mention this previously, but it's probably important to go back and remember that I can calculate the tension. So the tension is going to look like, T1 is going to look like M1A plus M1G. and T2 is going to equal m2g minus m2a. And so once I have the acceleration, I can come back up here and apply that and determine what the tension is.